Chapter 8, Introduction to Hypothesis Testing, Part 8. Now we'll discuss the influences on power, and we'll look at how these different variable changes, what we would expect the effects to be on power. So as effect size increases, power also increases, which makes sense, right? Effect size is the difference between m and mu. And again, by definition, what does power represent? It represents the probability of accurately rejecting the null hypothesis. So obviously, if we see a larger effect size, then we're going to reject the null, and the larger the effect, the more likely we're going to correctly reject the null hypothesis. Large sample size produce greater power, and again, we learned about that relationship in terms of our z-statistic, so we can apply that here as n increased, right, our standard error decreases and z increases. So if our z value increases, then we're going to have a greater likelihood of rejecting the null. Again, recognizing what power represents, so larger sample sizes are going to increase power. Using a one-tailed directional test increases power relative to a two-tailed test. And why is that the case? Well, if we think about the z values, let's say alpha at 5% for one-tailed, our z-score is 1.65, and I'm just going to use the positive values to illustrate this. If it's a two-tailed test, right, we have negative 1.96 and positive 1.96. Notice that the z-score is much higher, right, for two-tailed. This is one-tailed, this is two-tailed. So the area in the critical region is larger for a one-tailed versus a two-tailed test. That region is smaller because it's split between both tails, and obviously the z value is larger. Now let's talk about what decreases power. So when we reduce the alpha level, making the test more stringent, in other words, that reduces power. So again, it has to do with the shrinking of the critical region. So let's say a two-tailed test at 5%, and then if it's 1%, right, we see the decrease of the critical region, and as a result, the power is going to decrease. So again, implementing more stringent tests, meaning that we have a smaller alpha, we go from 5% to 1%, visually speaking, that decreases the critical region, decreases our likelihood of rejecting the null, and decreases our power. Using two-tailed tests decreases the power. So again, I've already discussed that when I spoke about this point, but again, if we are splitting that alpha into two tails, that critical region is smaller opposed to a one-tailed test, and that's also illustrated in the z-scores that we're seeing for any particular alpha, whether it's 1%, 5%, or 0.1%. So keep these the relationship between these variables in mind, and you'll have some problems that will help you better see that when you work out a problem. So don't just memorize this. You know, there are some homework problems that show you the influences that each of these variables have on power. So we're going to focus on one particular element, which is sample size, and see when we calculate power how changing the sample size changes the amount of power, the probability of accurately rejecting the null hypothesis. So figure 8.10 illustrates how shrinking sample size reduces power. So we're going to use the same values that we demonstrated in the previous video using figure 8.9, where we had a original population mu of 80 with a standard deviation equal to 10. So that's what we begin with. And then we have the scenario of no treatment effect if the null is true, and then the scenario on the right, which illustrates an 8-point treatment effect. and what the mu and standard deviation would be for those distributions. But what's different now is that we're saying we have a sample of 4 individuals. And so what do we expect in terms of the result on power? Is it going to increase or decrease? Well, the previous slide said that increasing sample size would increase power. So conversely, decreasing it is going to decrease power, and we're going to see that. And notice now this blue area, as we saw in figure 8.9, that blue area represents the power. So what do you see happening? Before it was the body. And now what area would we refer this as, or to? The body area between the mean and the z, or the tail? If you said the tail, that's correct. So notice how in the previous example it was the body, it was a large area of that treated population distribution, and now it's shrunk to now represent the tail. So we're going to calculate the power for this example, but I just wanted to go over the basics. Again, we're going to use alpha equal to 0.05, which is where we're getting these z values down here. As we did in the previous example, we're going to use those z values to generate what the minimum sample mean is required to reject the null. And then we're going to compute the probability of obtaining that sample mean in the treated population, and that will determine the power of this particular test. Before we move on, one other thing that I should point out that has changed: because sample size has changed, we should expect a change in the standard error opposed to the previous example in figure 8.9. So our standard error is equal to standard deviation over the square root of n. Standard error is equal to 10 divided by the square root of 4. 10 over 2 is equal to 5. So that's why we see this value change. In the previous figure, 8.9, the standard error is equal to 2. And again, we know that as n increases, standard error decreases and z increases. And in this case, we see that n decreased, so the standard error increased. It went from 2 to 5. So now using these values, let's walk through the example of changing sample size and comparing it to what we saw when sample size was equal to 25 and now equal to 4. So again, these are the values that were given. The original population average is equal to 80 with the standard deviation equal to 10. We're going to have select a random sample of 4 individuals, and given that they anticipate an 8-point treatment effect. Again, it's adding points. We expect an increase and a shift upward from the original mean. We can conclude that the anticipated sample mean is equal to 88. So again, starting with our original distribution with the mean equal to 80, and our standard deviation, standard error of the mean is equal to 5. So that's representative there. And we're going to use alpha equal to 0.05. So we'll create our critical region, and we know that that's equivalent of a z-score of negative 1.96 and positive 1.96. And what we're going to do now is solve for the sample mean here. In other words, what is the sample mean that is equivalent to 1.96 standard error units above the mean? So just as we did in the previous example, the first step would be to solve for m. Our equation is m is equal to mu plus or minus our standard error multiplied by our z value. We'll replace variables. M is equal to 80 plus or minus our standard error of equal to 5 multiplied by, we're going to use the positive version again because we're anticipating an increase. So m is equal to, in our calculators, 5 times 1.96 added to 80 should give us a sample mean equal to 89.8. So we can put that in here now. 89.8. In other words, we have to, given treatment, the sample mean should be greater than 89.8 to be in the critical region, enable us to reject the null hypothesis. So that's the first step. Again, ultimately what we want to do is calculate the power, the probability of accurately rejecting the null hypothesis. So the next step is to overlap the treated population distribution and see where this 89.8 resides in relation to the treated population. So the treated population mean is equal to 88. So let's look on our x-axis and see where that would reside. And we just identify the sample mean of 89.8, so it would be right about here. And that's the mean of our treated population, so 88. Notice how that's different from what we saw when we had a sample size of 25. Now things have changed because the sample has decreased significantly. And so again, this area over here, this little blue area, was the critical region for the original distribution, right? If there's a treatment effect, our sample mean would have to reside in that area. And now, given this idea that if the treatment did produce an 8-point treatment effect increase, then our new population mean would equal 88. And this value of 89.8 now represents the cutoff for what we would refer to as the body of the, excuse me, not the body, the tail. I didn't mean to confuse you. It's the tail of this particular distribution, and it is representative. The power is what I meant to say, the power, not the body. So now we would state this as, what's the probability of obtaining a sample mean greater than 89.8 in the treated population? To answer this, we're going to need to convert that sample mean into a z-score. So z is equal to m minus mu divided by our standard error. Z is equal to 89.8 minus, and again, it's the treated population, which is why I'm writing in red, and therefore I'll change this over here and make that mean 88. So we keep it separate. And then divide by our standard error, which is the same for the treated population as the untreated, divide by 5. So our z value is equal to, in our calculators, 89.8 minus 88 divided by 5, and we get a z-score of 0.36. And again, notice it's positive because we are to the right of this value of 88. We're to the right. So this 89.8 is equivalent to a z-score of 0.36, or 0.36 standard error units above the mean. So now we can convert that original probability statement to now read the probability of obtaining a z-value greater than positive 0.36. And again, given the location, given that this is the center and this is the cutoff that we're talking about, that line, we understand this to represent the tail of the distribution. It's no longer the body, as I indicated. It's not always going to be the same. And so this is a great example to contrast with the previous example where the power was represented by the body of the distribution. In this case, the power is represented by the tail of the distribution. Now, to answer our question, our probability statement here, and to calculate the power for this example, all we need to do is utilize our unit normal table and find the proportion in the tail for a z-score of 0.36. So here's our unit normal table, our z-score of 0.36. The area in the tail is 0.3594, or 35.94%. So let's go back to our example to put this into perspective and answer our final question and determine what the power is equal to. So we've just answered this probability statement. It's equal to 0.3594 or 35.94. So we've just calculated the power. The probability of accurately rejecting the null if our sample size is equal to 4 is 35.94%. Or we would say that 35.94% of samples, treated samples, would reside or be greater than 89.8 and enable us to reject the null hypothesis. So notice the power has decreased significantly. When the sample size was equal to 25, our power was, I believe, 97%. Yes, it was 97.93%. It was huge. It was a very high likelihood of accurately rejecting the null. With a much smaller sample size, that power has significantly decreased. It went from 97% to 35%, less than a 50% chance. And whenever your power is less than 50%, there's no reason to go forward with your research. Again, this is why we would conduct a test of power prior to engaging in research. We want to know how successful we're going to be. Researchers always want to be successful. They always want to be able to reject the null hypothesis. So if a test of power illustrates that you will not be successful, there's no point in going forward. Now, this makes sense. The sample size of 4 is not representative of a population, so it would be very hard to draw statistical conclusions or significant statistical conclusions given such a small sample. It makes sense that it should be harder to reject the null hypothesis when we have such a small sample. We want large representative samples so that we can draw our conclusions based on a sample and apply them to a population. And it's very unlikely that 4 individuals are going to be representative of all the characteristics that are displayed in a larger population. So again, this example, in contrast to the previous video example, helps us see the influences of sample size on power and also the ability to reject the null hypothesis. So our ability to reject the null hypothesis is significantly decreased because we're working with a much smaller sample size. And just to clarify again, this statement helps us solve for power. So our power, our final answer for this problem would be 34.94% chance that we would accurately reject the null hypothesis given a sample size equal to 4, and still using a treatment effect size of 8 points. So we'll end this video with a learning check. The power of a statistical test is the probability of, again, question of definition, and we've been talking about this quite a bit for the last 2 videos. So given these responses, rejecting a true null hypothesis, supporting the true null hypothesis, rejecting a false null hypothesis, supporting a false null hypothesis. So again, I told you the definition of power is the probability of accurately rejecting the null hypothesis. So if we're rejecting it and if we're accurately doing so, then our answer for this particular question would be, we would recognize that power represents rejecting a false null. Again, the null says nothing is happening. So if that's false, we're then affirming something is happening, and we're doing it based on, we're accurately drawing that conclusion based on a certain probability that's defined by power, or the calculation that we come up with when we go through the process of computing power. Next, decide if the following statements are true or false. First, Cohen's d is used because alone a hypothesis test does not measure the size of the treatment effect. And this is true. We learned that Cohen's d is a measure of effect, and we utilize it because by looking at the equation, it removes the influences of sample size. Again, our test statistic z is equal to m minus mu over standard error. And standard error is equal to standard deviation over square root of n. And we have spoken extensively about the influences of n. So again, Cohen's d helps us better measure the treatment effect that is occurring. And we express that treatment effect in standard deviation units. Next, lowering the alpha level from 5% or 0.05 to 0.01 or 1% will decrease. So we're lowering it from 5 to 1, so that becomes, the critical region becomes smaller. will increase the power of a statistical test. So again, just as I said that the critical region is decreasing, we would anticipate that the power would also decrease. So this is false. So it would actually decrease the power because the critical region has become smaller. And that concludes the final lecture for Chapter 8. Very long chapter. I understand a lot of information, but all of what we've learned in Chapter 8 will set us up to better understand the T statistics that represent Chapters 9, 10, 11. So Chapter 8 is essential to learn the new material in Chapters 9, 10, and 11. And if you can master Chapter 8, Chapters 9, 10, and 11 will be a breeze. So again, that concludes the lecture series for Chapter 8.